Okay, good morning, everyone. So this is the tutorial for week 3. And by now, actually week 3 and week 4. So we will do like half of this today. So if you download from the Moodle, you will see this set of problems. So now we start working on it one by one. Okay. So now let me work on a piece of paper. So now, question number 1. So what is the norm of a vector? So now, if you remember, so the norm of the vector x, the one norm, is just the absolute value of all the component, and you sum it up. Okay. And then the two norm of the vector x, you just take the square of each component, you sum it up, and then do not forget to take the square root of the sum. And then the last one is the infinity norm. So, so infinity norm, then you just have a max, and do not forget the absolute value of x1, x2, because it could be a negative number up to xn. Max value of those things. Okay. So this is just the definition. So how about now? How do you plot the unit disk? Well, this one we can plot only an R2 only, so maybe just restrict to R2. Okay. And of all elements, that the one norm less than or equal 1. So how do I plot it? So this one, if I write down, x is a vector of x1, x2, right? Then, I mean, this condition just means that absolute of x1 plus absolute of x2 less than or equal 1. So how do you plot it on the plane? So this is the plane here. So this is x1, this is x2. So what is the region? What is the region on the plane? Any guess? Any rough guess? So what region? A diamond, yes. So the diamond. And what is the vertices of the diamond? So the diamond is the correct one, yeah. So now why is it a diamond? Because you see this one, you can split it into 4 cases. So now it will be, will be x1 plus x2 less or equal 1. If x1 positive, x2 positive, right? And so what is this region? So x1 plus x2 less or equal 1. It's just this region, right? x1, x2 are positive. So this just this region. This is 1 and this is 1. Okay. And then, I mean, it will be x1 minus x2 less or equal 1. If x1 is positive, x2 is negative, right? Because remember the absolute value, of a negative number, you just take minus of that, so it becomes positive, right? And then, so x1 positive, x2 negative will be this region. So if you plot this one, you get the second region. Minus 1 here. Okay. And then the third region is so you can do the third region, and it will be minus x1 plus x2 less or equal 1. So this is when x1 is negative, x2 positive, right? And then you get this region. minus 1 here. Yeah. And then and so on. So you got minus x1 minus x2 less than or equal 1, and x1 less than 0, x2 less than 0. And then you get this region. So it's a diamond shape. Okay, and this is minus 1 plus 1 here, minus 1 plus 1. Okay. And now what happened if I change the norm? So now B2 is the in R3, it is a rotated group. Yeah. So well, so it will be a diamond in R3. It's a diamond. Yes, it's you can say that it's a rotated group. Yes, but it look like, you know, in R3, then you have to take on the indices 1 and minus 1 on the x, y, z, right? And you just connect the on the edges. Yeah? So in R3, it looks like something like, well, you have to make all the vertices here like this. It's a bit hard to visualize, yeah. But then you connect on the dots, yeah. So it will be. I'm not a very good painter in R3. Okay, I'm not a very good drawer, but you can imagine, right? So it will be a diamond in R3. Okay, so try to plot it in R3, but you get the idea, right? So I'm not a very good sketcher here. So now suppose now in the case of the two norm, then you got B2 is on the vector, and that satisfies this two norm less than or equal 1. Okay, so then this one is just x1 comma x2 and x1 square plus x2 square. Take the square root less than 1, so you square it, and it's still less than or equal 1. So what is the shape of this one, of this region? What is the shape of the region x1 square plus x2 square? Yes, just a circle, right? Yeah, so it's just a disk, because you take everything inside the circle. This become a disk. So x2 here, x1 here, and everything inside. So you plot a circle on the boundary, and then everything inside is the region here, because remember less than or equal. Okay. So in R3, yes, it's the sphere. Yes. So in R3, it will become the sphere. Now it's a bit tricky to plot, but you can imagine. Yeah. So in R3, it will become a sphere. Okay. And now the last case will be infinity norm. So now if we change the norm again, so now this is the last one will be to take B infinity is x in R2, and infinity norm of x is less than or equal 1. So it will be x1, x2, and x1 max of absolute value of x1, x2 less than or equal 1. Okay, so what region is this one? So what region that satisfies this condition? What region satisfies this condition? Anyone? Any guess? A square, yeah. So a square, and it will be a square of the range minus 1 to 1 here. and minus 1 to 1 here. So everything in this square will satisfy the condition, right? I mean, every so okay, so then this region will be the square, right? And then now the next one will be show that the norm in the two norm is less than or equal the norm of x in the one norm less than the square root n time the two norm vector x. Okay. So how do you prove that? Well, so if you take the two norm of the vector x, okay, and you square it, then what do you have? And you just have x1 square plus x2 square plus dot, 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 up to xn square, right? Okay. So now the next step would be I just make it less than or equal x1 square plus x2 square plus up to xn square. But now I just add, extra positive term. So what is the terms I'm going to add? I will add the cross term. So x1, x2 in absolute value. Okay. And then x1, x3. Okay. And so on up to, x1, xn, and then plus x2, x3, and so on, So you see, I just add on the cross term. Cross term xi, xj in absolute value, and I less than j. Okay. And if you remember, the identity, this one will equal x1 plus x2 in absolute value plus up to xn, everything square. Okay. So remember this identity, right? So this identity, maybe you've seen it somewhere. So if you square, this one, then you get x1 square plus x2 square plus xn square, right? Then you get all the cross term. Okay, maybe twice the cross term when you order the index I less than j. Okay. So think about like x1 plus x2 square, then you got x1 square plus x2 square plus 2x1 x2. Okay, so that is a similar space. But then what is this one? So this one is nothing but one norm of the vector x square. Okay, so that is how I prove it. So how I prove the two norm. See, we follow from here. So the two norm of vector x, right, is less than or equal this, and less than or equal, the one norm square. So therefore, the two norm of the vector x. So this one is always true, okay, for any vector x. So the two norm is less than or equal to one norm. Okay. And now that is, I just prove only one inequality. Yeah, I just prove this inequality. Maybe this is, we call it A. Yeah, so A is right here. But we need to prove B as well. Okay, so now how do I prove B? So B, before I prove B, I want to introduce you the Cauchy-Schwarz inequality. So maybe B like this, yeah. So introduce Cauchy-Schwarz inequality. So have you seen this inequality before? So A is in Rn and B is in two vectors in Rn, yeah. And when you take the dot product of the two vectors, then it will less than or equal the two norm of vector A times the two norm of vector B. Okay. So why is that? Well, because again, Cauchy, he's a French mathematician, and so I think it's German mathematician. They came up with this inequality maybe 300, 400 years ago. But essentially, why is this inequality is correct? Because, you know, if you remember your algebra, so when you have two vectors, A dot B, then you can write this dot product as the length of A, what happened to be the two norm of A times the length of B, this is the two norm of B times the cosine of the angle between the two vectors. So you have A here and B here. Okay, so maybe you've seen it somewhere. I mean, sorry, theta here, yeah. And see, because cosine theta is always less than or equal 1. Yeah, so then therefore this one less than or equal the, well, maybe say that this is because, yeah. So this is a very simple proof. Okay, so well, I assume that you remember the formula for the dot product. Yeah. So the dot product can be interpreted in this way. Yeah. Okay, so now back to the inequality. So how do I show that the one norm of vector x? Okay. So how do I choose A and B? So then I can apply this inequality. So I want to show the one norm of vector x, right? Now, if I want A, you know, to be the one norm vector x, maybe let me make the vector A to be like this. So x1 absolute value the first component vector x, absolute value second component up to xn, right? So now what vector B should I choose? So that A dot B will become the one norm of the vector x. Anyone? So what vector B should I choose? So that A dot B will become the one norm of the vector x. On ones, yes, correct, yes. So you choose B 1, 1, 1, 1, 1 up to the last one. Then A dot B is just the, you know, I mean the sum of x1 plus x2 and absolute value up to xn, right? Yeah, and you see it will less than or equal. Now what is the two norm of A? Well, the two norm of A will just equal the two norm of vector x, yeah. And now what is the two norm of B? Square root n, yes. So because, you know, you just take 1, 1, 1 n time and the square root. So then this one give you square root n. Okay, so this is how we prove it. So this one is the one norm of vector x will be less than or equal square root n times the two norm vector x. Okay, so the other two inequalities I just leave it exercise, you know, because we don't have time. So now question number 2. So prove. So question number 2, prove that 1 over n condition number the two norm of a matrix A less than or equal the condition number in the one norm of the matrix A, less than or equal the n times the condition number in the two norm of the matrix A. Okay. So now what is, so now let we prove number C first. Okay, this inequality first, yeah, and then we can prove the other one. Yeah, so now let's prove number C. Yeah. So first, what is the condition number in the two norm? Well, condition number in the two norm is just I mean the norm of the matrix in the two norm times the norm of A inverse in the two norm, right? Yeah. And now, well, you know, condition number in the one norm, then you just replace this one by the one norm, right? But now if I look at the norm of the matrix A, right, the two norm, right, then by definition, this two norm will be max of AV in the two norm over V, you know, in the two norm, and max over V non-zero. Okay. But now remember that we have AV, right? The two norm. Yeah. By the one you just show, I mean the inequality before, the two norm is just less than or equal to one norm. Right? So we show this in the previous question. Remember AV is a vector. So a vector, then you take the two norm is always less than or equal to one norm. Okay. And then if I take the norm of the vector V in the two norm, yeah, then it's always bigger than 1 over square root n, the one norm times the one norm, right, of the vector V. Right, we proved it before, right? So we proved the one norm less than or equal square root n times square root of square root n times the two norm. So I just write in a reverse direction like this. So why is that? Well, because I want to take the ratio. So if I take the ratio, then, you know, assume that the vector is non-zero, yeah? Then I got this ratio. So AV not two norm over V two norm will be less than or equal, right? AV one norm over V one norm. Yeah. Okay, so that's I can do it. So assume that V non-zero. So V are not a zero vectors. Otherwise, you cannot divide like this. Yeah. Now I forgot 1 over square root n. So 1 over square root n here. It will be square root n here. Okay. Yeah. Flip it. Yeah. Okay. And then now what do I do? So now, so remember I have I have something like this, yeah. And now what I want is I want to take the maximal over the right hand side. So now AV, the two norm will let over V in the two norm will less than square root n maximal of AV one norm over V one norm, right? V non-zero. Okay. So this one is for any V, right? So then you take it equal, I mean less or equal for any V. Then you take maximal of the right hand side, and then this one is nothing but the one norm of the matrix. Remember the definition, right? So this one is just the one norm of the matrix A, and times square root n, right? Then you have AV two norm over V like this, yeah. And now I take the maximal of every V on the left. Okay, so now I take the max of all the V not zero on the left. Then it's still less than or equal square root n times the one norm of A. Okay. And so then this one, by definition, nothing but the two norm of the matrix A less than or equal square root n times the one norm of matrix A. Okay, so similarly you can do it for A inverse. Okay, so you have A inverse. You take the two norm of the matrix A inverse, then it less than or equal square root n of A inverse, one norm. And now you just multiply. Okay, so now you multiply star and double star, right? So star, so multiply star and double star. Then the left just give you the condition number in the two norm of the matrix A. And the right hand side just give you n times the condition number of matrix A in the one norm. Okay, so that is how we prove it. Okay. So now it is an exercise for you to prove the other inequality. Okay, just use the same trick, but now you have to reverse the inequality. So remember, so this is the only the first inequality. We show the second inequality. You have to show that kappa 1 less than or equal n kappa 2. Okay, so it's an exercise for you to do it. Okay. So any question about this one? So everything is okay, yeah? Can you please go over the lines where you change to max? You mean here, this line? Yeah. Okay. So initially, right, you have this one, right? You have this ratio. So this one is true for any vector v. Yeah. Agree? So then you can take the max of the right hand side. And it's still correct. Yeah. And then if you take the max, then it's become the one norm. And then you see now the upper bound doesn't depend on the vector v anymore, right? So it's always true for any vector v. So this one is true for all vector v, non-zero. Then you can take the max on the left-hand side. And then when you take the max on the left-hand side, then I mean you got the two norm, the matrix A. Okay. So it's a bit tedious, but that is how we prove it. Somebody can say that, why don't you take the max of the left and the right hand side at the same time? Well, I mean, you can do that, but it's a bit sloppy because, I mean, when you take the max the maximum can obtain from some different vectors. Okay, so we are careful that we take the max on the right hand side first, then you take the max on the left hand side. Okay, roughly speaking, you know, I mean, it's just a consequence of this inequality, right? And you take the max of the both the left and the right hand side. But we have to be careful that we take the max on the right hand side first, then we settle down, then we take the max on the left hand side. Okay. Okay, so now we move on to the next question. So the next question is how you, so there's other inequalities, you just prove it. Okay, it's an exercise, but you use the same techniques. So now I'm going to prove question number 3. And it's a bit strange because you haven't seen the norm of the matrix before, you know, but you get used to it. And if you study year 3 and year 4, then you will see it again, you know. So, okay, so now suppose I have 2 matrices. Then if I take the norm, so this is any norm, okay, then we will less than or equal the, so the product, take the norm, the product will less than the product of the 2 norms. Okay, for any norm. Yeah. So how do we prove that? So now we know AB, the norm AB, by the definition is just a max of ABV, take the norm over V for any non-zero vectors. Okay, so that's a definition. But now remember you have this property. So you have so suppose you have now the claim is yeah, is you have AV, well not AV but maybe AY. Okay, when you take the norm, it will less or equal the norm of A times the norm of Y. Okay, so for all vector Y not 0. Okay, so why is that? Well, actually, if it's 0, then we have an equality, but we just assume that is a non-zero vectors. Yeah. So why is that? Well, now if I have a non-zero vector Y. Okay, so now this one is the proof of the claim. Yeah. So suppose I have a vector Y, right? Then I mean a non-zero vector Y. Then I can take this ratio. Okay, so assume that you have a non-zero vector Y, right? And you see, I mean, this ratio is on Y less or equal maximum value of on possibility, right? I mean you have a vector, right? This is a fixed vector of Y, but here if you take the maximal over on the possibility, then this ratio definitely less than this. You know, you take one element in the population, so it will less than the max of on the population, right? And then what is this one? So this one is nothing but the norm of A, by the definition, right? So you have AY norm over Y norm less than or equal this, and then you cross multiply and you get exactly what you want, right? So we stop here, right? So now go back to the proof. So now I have AB norm is max of B non-zero. Okay, ABV over V. Yeah. But now I apply the claim for this vector y. Right, so I label BV to be the vector y. Remember, B is a matrix multiplied by a vector, give you a vector. Then this one will less than or equal the norm of A times the norm of BV over V. Well, still correct with when you take the max. Yeah, so this one is inside the max, but it's still correct. Yeah. And now, if you look at this one, so the max over V, but then the norm of A doesn't depend on V anymore. So you can take it outside, right? Take it outside the max. So you have the norm of A here, and then you have a max of V, BV, the norm over V, norm, right? And so this one is what? So what is this quantity? Max of BV norm over V norm. So what is this quantity? Yes, just the norm of V. Yes, by definition. So this is a normal of matrix V. Okay, so that is how you prove it. Okay, so now the next step is I want to prove the condition number of a product of two matrices will less than the product of two condition number. Okay, and why is that? Well, if you take the definition, and this one, when we have no subscript, it means that it's true for any norm. Okay, so when the norm doesn't have any subscript, it's true for any norm. P could be infinity, could be 1, could be 2, 3, 4, 5, whatever. Yeah. Okay, so now condition number of AB is just AB norm times AB inverse. Okay, so here we have to assume that A inverse, B inverse exists. Okay, otherwise you cannot take this. And remember, in linear algebra, if you take inverse of a product, then it will become inverse of the first, inverse second matrix times the inverse of the first matrix. Okay, so this one just from linear algebra. Yeah. So then this one will become AB norm times B inverse, A inverse norm, right? And now we just apply what we just proved. So AB norm is less than or equal the product of the two norms. Yeah. So will be the product of A times B, and this is the product of B inverse, A inverse, right? And now, what is this one? What is the norm B times the norm of B inverse? What is that? No, it's not 1. No. Now, B times B inverse is identity. Yes, condition number of B. Yes. So this one is just condition number of B, right? And then A norm times A inverse norm give you condition number of A. Okay, so this norm A times the norm A inverse gives you the condition number of B. So that is of A. Yeah? So that is how you prove the inequality. Okay. Okay, so now the next one is the condition number, well, the norm of identity matrix. So now if you take identity matrix, So take identity matrix, okay? Then the claim is the norm of identity matrix is equal 1. Well, I mean the norm of identity matrix is just max of IV over V. Norm, right? Any norm. But identity matrix multiplied by a vector, then you just get the same vector, right? You don't change it. So and so this one is maximal of 1. All of them, all of the V give you 1. So this one just give you 1 all the time. Okay, so just follow from the definition. And now condition number of identity is 1. Well, because I inverse is the same as I, right? The identity matrix multiply, you take inverse just the same as I. So I inverse the norm is just equal 1. So norm of I is 1. So therefore the condition number of I is just equal 1. Okay, 1 times 1. Yeah. Okay, so now the fourth property is the condition number of a scalar multiplied by matrix A is the condition number of A. Okay, for any non-zero scalar. Well, I mean, you just take the definition. So condition number of A is just the norm of mu A times the norm of mu A inverse. Okay. And we know that because the norm of a matrix is a norm, right? So it satisfies the property that if you multiply by a scalar, you can take out the scalar, or you have to take out the absolute value, right? Then you got a norm of A here, and this one you get out 1 over mu, and this one is just A inverse. Okay, so mu here cancel with 1 over mu, and you got A times A inverse, the norm. So then you just got the condition number of A again. Okay. And the last, I mean, sorry, not the last, the fifth one is condition number of A inverse. Is the same as the condition number of A. So why is that? Why is that? Why is that? Why is that? Anyone? Why the condition number of A inverse? Yeah, the expansion are the same. You just swap, yes, exactly. So this one is just A inverse norm times A, right? And this one is just A norm times A inverse, yeah. So I assume that A inverse exists, yeah. So that is how you prove it. And now the last property. So the last property is interesting. So condition number of a matrix is always greater or equal to 1. Okay. So for any non-singular matrix. Okay, so the hint is you have to use the 3 properties. So you have to use the 3 properties we had before. So kappa of a product less than kappa of A times kappa of B. Kappa of identity is 1. And kappa of A inverse equal kappa of A. So you have to use those properties. I think this is property number 5. Right? Oh, this one number 6. No, this one number 6. So this is a property number 2. Yeah. So this is number 2, and this is number. So this is the number 2, and this is number 3. And this is number 5. So how do you use those 3 properties to show that the condition number of a matrix is greater or equal to 1? Anyone? You can prove it directly, but it's a bit tough. I mean, the hints, you just use those three properties. Then you can make a conclusion. Any guess? How do you use those 3 properties to prove the last property? Anyone? So the hint is you just use, some special case of the second property. So just use some special matrix B. Then you can prove the last property. Anyone? Are you still there or you're drinking coffee? Can I move the page up? Yes, so you move the page up like this. You mean move down or move up? Like this. Yes, if you take B to be A inverse, yeah. So if you take B to be A inverse in the second property, then what you have is kappa of A times A inverse. Okay. The less than or equal kappa A times kappa A inverse, right? And A times A inverse is just an identity matrix. And kappa A and kappa A inverse are the same. So this one is just kappa A squared. Now you got kappa A squared greater or equal 1. Okay, so by property 3. So therefore, take the square root, then the condition number is always greater or equal 1. So if you have a numerical computation that give you the condition number less than 1, then there's something wrong. Okay, so condition number of a matrix always greater or equal 1. Yeah. Okay, so now we move to the next question. So that is the property of a condition number. And now we go to question number 4. So a symmetric matrix has those eigenvalues. So we just worry about the largest, okay, and then the smallest. Yeah. And now the first question said that why A is non-singular? Well, A is non-singular because what? Because the determinant, right, of A is the product of all the eigenvalues. And you see that all the eigenvalues are positive. So this one is positive. So the product of the eigenvalues equal the determinant. And if the determinant is non-zero, then we have a non-singular matrix. So this one is just from linear algebra. And now what is the condition number and the 2 norm? So the condition number and the 2 norm of the matrix A will be now, yeah, determinant not 0, then you have a non-singular matrix. So in this case, it's positive, so therefore non-zero. Okay. So in the condition number, the 2 norm, take just the largest eigenvalue in the absolute value over the smallest eigenvalues. Okay, so this is a symmetric matrix case, yeah. And now lambda max will be 1004.2 and divided by lambda mean. So then you got about 2,008,400. Okay. So this, just plug it in the calculator. And now, what is the relative errors in the inputs A and B? So this one is number 2. So the relative errors in B, well, maybe relative errors in A first, yeah. So relative errors in A will be machined by epsilon, because if you look at the question, you know, you will see the phrase A is known exactly. So it's known exactly, it just means that you can get up to the machine errors. Okay. Good question. How do we know it's a two norm? Well, I think the question doesn't say, but it should be the two norm, because you see, in order to find the one norm and infinity norm, you have to know the entries of the matrix. And here you know only the eigenvalues. And you know the formula for getting the norm when you know the eigenvalues is only the two norm. Okay, so maybe I should put in the question. Estimate the condition number of A in a two norm. But you know, I mean, you cannot estimate in other norms, yeah. No other information. Isn't the formula exact? So good point. Yes. So yeah, so you can say that computes, yes, the formula is exact, yes. Yes, you get a point, yes. Okay. Okay, so now but you know, remember that even you have eigenvalues here, right? This one is still subject to machine errors, right? So you can say that there's still, like, with respect, you know, when you know this, still with respect to machine errors. Okay, so there's still some errors, you know, because you cannot do anything. Yeah. Okay, so now the condition number, we agree on that. So now, so when we say matrix A is known exactly, then the relative error just is epsilon. Epsilon is, remember, is just 2.2 10 to the minus. So we have this. Okay. And relative errors for B. Well, the relative errors for B will be I don't know. So now, is it okay now, or it's okay, right? Okay, so maybe the internet just dropped out, but you know now the relative errors for B is less than 0.5 10 to the minus 6. Because why is that? Because there's a phrase. So if you look into the question again, in the sentences, is measure to 6 significant figures. Okay, so whenever you have B is measured to some significant figures, then the relative error is less than 0.5 times 10 to the minus the number of significant figures. Okay, so this is an IEEE definition. So we mentioned that in chapter 2 already. So if you look carefully, you will see it. Okay. So when you say B is measured up to 6 significant figures, then just mean that the relative errors of B less than 0.5, 10 to the minus the number of significant figures. So now estimate the relative errors in X. So when you compute Ix equal B, well, so this one is the theorem in chapter 3. I believe that the theorem is 3.1.7. So check theorem 3.1.7, okay? So the relative errors in X no less than or equal the condition number of the matrix times the relative errors in the matrix A plus the relative errors in the vector B. Okay, so now everything you have in numbers already. So this one is 2,008,400. And then this one you have it here already. So 2.2, 10 to the minus 16. And this one is 0.5. So this one less than 10 to the minus 6. Okay, so you put in the calculator and you get about 1.0042. So the relative errors is 1 point something. So is it a small or big number? So relative errors is 1 point something. Is it a big? Yeah, because relative errors is measured like the percent, right? So this is like 100%, right? More than 100%. So there is no confidence in the answer. So no confidence in the answer of X, yeah. Okay, because the relative error is bigger than 1. Okay. So that is what we can do. I think we cannot do question number 5. And we have to stop here and let me stop the recording.